In this video, we're going to walk through a demonstration of how we can leverage various capabilities across the Labelbox platform to support and accelerate an image segmentation use case. In particular, we're going to look at how we can use Labelbox to explore and curate relevant data from an archive of images, accelerate the labeling process, support evaluation of our custom-trained models, and improve the speed at which we iterate until we reach adequate model performance for deploying into production. We'll look at a real-world use case where a customer in the manufacturing sector may wish to leverage image segmentation techniques to improve overall quality control by analysing images of products as they roll off of a production line. We'll join here, where we have various images uploaded showing different manufactured products. For details around how to upload images to Labelbox, you can check out our online documentation. However, if we may be interested in developing a solution that looks at a particular product coming from a particular facility or production line, to do so, we can narrow down on relevant data using catalog similarity search. For example, if we're interested in this particular product here, a cast steel ball bearing, we may be able to select multiple similar images to provide as anchor images. Having done so, we can then click the Similar to Selection option at the top. What this will do is to search for similar image embeddings that sit behind catalog. We can see in the first instance we have still a very large volume of data rows available to us. Therefore, we may wish to increase the overall similarity threshold at the top until we narrow down on a suitable subset of our data. At this particular threshold here, we can see we've narrowed down to just 4,000 images. A quick scroll through shows a good degree of uniformity across the images that we're looking at and provides us with confidence that we are looking at the same product in each instance. Having done so, there are now various ways that we can save or tag these data rows in order to come back to them later on. First of all, we can do select all, and at the Manage Selection option at the top, we can add metadata to this. We could add something around, say, the industry that it exists within, say casting manufacturing. Having clicked Save, this has added a metadata tag to each of these data rows, which we could come back to later on by searching under the metadata option at the top. An alternative approach are to save all of these data rows as a slice. Again, we can name this something appropriate, such as casting manufacturing. If required, we can add a description around this slice and we can click Save. The advantage of a slice is that whatever filters have been applied at the top, as and when more data is ingested into Labelbox, these will automatically be filtered into the appropriate slice on the left-hand side. What this allows us to do is at any stage to come back to the slice and to narrow down to those data rows which meet the criteria. We can add additional criteria by adding aspects as to, say, the data set that it comes from, any metadata, or indeed the type of data we're looking at from image to text. It gives complete flexibility of how we set up our slices and how we curate data over time to ensure that we have relevant subsets for various use cases we're working with. Having narrowed down on a subset of our data that we're interested in taking forward as part of this use case, we're now in a position to set up an Annotate project and to begin labeling various aspects of our images. However, before doing so, we first need to understand what attributes it is that we're interested in labeling. To do so, we can easily visualize our various data rows within Catalog and do a visual exploration to understand what defects may exist. Selecting into this particular data row, we can see the presence of a large chip on the left-hand side of the face. Additionally, in certain instances such as this one, there are also frayed edges around the outside of our product. We'll take a note of these two defects as we can include these in our ontology when we come to set up our Annotate project. Having done appropriate visualization to understand the various defects that we're interested in capturing, we're now in a position to set up our ontology and subsequently set up an Annotate project. To do so, we can navigate to the Schema tab on the left-hand side, making sure that we've selected Ontology at the top, and we can click Create New. The first thing we're going to have to do is to identify the media type that each of our data rows are. In this case, we're dealing with image data, so we can go ahead and select Image at the top. We then name it something appropriate, such as Defects for casting, and we can begin to add both objects. These are individual instances within an image that we're interested in tagging, and classifications, such as an overall classification for the image. As identified before, we have chips. We need to make sure that we're selecting segmentation as the type of annotation, and we have frayed edges. And again, we'll select segmentation. One other overall classification we may be interested in is the severity of the overall defects. We can name it severity, and we can have options of radio, checklist, or text. Radio is just a single option from a drop-down, whilst checklist allows multiple options. Free text is exactly what it says. Select radio because in this instance there is only one severity class that we want to apply, and we can define various options: low, medium, and high. Having done so, we can review our overall ontology, and once comfortable, we can create it. Now that we've set up our ontology, the next stage is to set up our Annotate project. Navigate to the Annotate tab on the left-hand side. We can select New Project. Again, we're dealing with image data in this case, so we can select Image, name it something appropriate. If required, provide a description, and then we can click Save. Now that our overall project is set up, the next thing we need to do is to add the ontology that we created a short while ago. We can select Defect Casting, and then we can click Save. Once our Annotate project is appropriately set up and we've added the relevant ontology, the final thing we need to do is to add our data. To do so, we select the Add Data option, which will take us back to Catalog, where we can navigate to the slice that we created earlier. We then have the option Select All, and we will in this case use the sampling functionality. At present, we don't necessarily need to label all 4,000 images in the first instance, but we can take a subset of this, add this to our Annotate project, and use that to train the first iteration of our model. To do so, we can select Sample. We can then select the appropriate project. In this case, it's defaulted to the one we've just created. And we can define the number of data rows that we want to sample. Let's say 1,000 in this case. We can change the data row priority, which influences the order in which data rows are set up. We'll make this a batch priority 1. And once we're comfortable, we can then click Submit. Doing so will randomly sample from the 4,000 data rows within our slice, 1,000 to pass to our Annotate project, which we can then begin to annotate. Navigating back to our project, we can see once the data rows are passed, our project is now set up and ready to start labeling. Before we do so, let's step into the workflows. This is the default workflow that is automatically set up whenever you establish an Annotate project. Talking through the various buckets, all new data rows land in this initial labeling task. As we can see, we have the 1,000 sample that we just created. After being tagged by a labeler, they will fall into review for a reviewer to go through and approve before falling into done. At any point, if there's issues that the reviewer spots with the initial labeling, they can reject the data row, move it back to rework for a labeler to go in, reevaluate and relabel each data row. There's also the ability to add new tasks, so you can configure this workflow in any way that suits your use case. However, in this case, we'll stick with the default workflow established. Navigating back to the Overview tab on the left-hand side, we can then select the option to start labeling. Doing so will bring up the Annotate UI. On the left-hand side, we have the various attributes about the image that we captured within our ontology. These are the object, i.e. the defects, chips and frayed edges, and the overall image classification, i.e. the severity, low, medium or high. On the right-hand side, we have a data row visualized for us, and in this particular instance, we can see two small defects visible on the face. In this case, we have two chips. To tag these, we can navigate to the left-hand side, and we can select the chips option. One thing which we can then touch on is the auto segment capability within the Annotate UI. If we navigate to the top here, we can select the option for auto segment. This makes use of foundation models in the back end in order to allow us simply to draw a bounding box around each of our defects of interest and for a segment mask to be automatically calculated for us. We can see on the left we have one instance of a chip recorded. We can repeat this process. This time around, however, we're going to make use of hotkeys. Next to our objects and classification of interest, we can see the numbers 1, 2 and 3. Simply tagging 1 on our keyboard will activate chips, and up here we can see the option R, which will allow us to activate auto segment. This helps accelerate the rate at which labelers can annotate individual data rows. Again, we can get the segmentation mask for that particular chip, and the last thing to do here is tag the severity. Overall, there's small chips on the face of it, there's no frayed edges, so we can say the severity of the defect here is low. Once we've appropriately tagged our data row, we can click Submit to add these to our queue. We can continue in this vein. In this case here, we have just the one chip. So again, we can make use of hotkeys, clicking 1, clicking R. We can draw the bounding box around the object of interest. We have our mask computed for us, and again, we can click Severity Low. In this particular instance, we have multiple defects visible to us. First of all, again, we can go Chips, and we can draw a bounding box around that chip. However, this time round, we also have an instance of a frayed edge. To do so, let's select the frayed edge option. Here, we might have to build up the overall segment mask in small sections, as seen here. In this case, we'll say the severity is high, given the presence of the frayed edge, and we can click Submit. You will eventually reach the stage where you have sufficient data for training the first iteration of your model. In our case, we've labelled and reviewed 1,000 data rows which now sit within the Done bucket. We're in a position to extract these for model training. To do so, the first step is to set up a model experiment. Navigating to the Model tab, we can go to Experiment and we can do Create New Model Experiment. We can name this something appropriate such as Defect Detection, and we can personalise it with a logo and a description as required. Selecting Next will then be prompted to select the ontology that we created earlier, Defect Casting, and we can select the project associated with it, Defect Tagging. We'll see here we have 1,000 data rows identified within our Done bucket, and we can go ahead and create our model. Having done so, the next stage is to select a model run. Model runs allow us to track over time the various datasets used to train our model and the overall model performance, allowing us to compare model runs against one another to identify whether or not we're making the intended progress. First, we'll set up our first model run, name it something appropriate such as Model Run 1, and then we can define the test, train and validate splits. The default will be 80-10-10. You can change this as required. However, in our case, we'll stick with the default. It may take a few moments, but after our model run is configured, we'll have visualizations of each of our data rows. We can select each data row to see the annotations associated with each one, such as the chip and the frayed edges. On the left-hand side, we can see our train, validate and test splits, and we're now in a position to export our annotations for training our model. To do so, we can navigate to the top right hand side, copy model run ID, and paste this into our Python notebook. We'll then use the Labelbox API to extract each of our annotations, form our data set, and train our custom model. In our Python notebook, we can paste the model run ID as required here, making sure to load the Labelbox API package. And then within a few lines of code, we can easily extract our ontology, as so, and we can extract our annotations as follows. Doing so, we'll create a JSON object where we can see each of our data rows, the overall global key, and the annotations, in this case, segmentation mask for the likes of chip and frayed edge. We can now appropriately manipulate this data to get it into a format for training whatever model of our choosing. In my case, I chose to train a YOLO segmentation model. After getting my annotation data in an appropriate format for the training, I then execute my training using the following lines of code. Once my model is trained, I can then use it to run inference on the data rows as follows, and then I choose to upload these data row predictions back to my model run for comparison against the ground truth. I do so here, creating my annotations, and then within a few lines of code, I can upload my predictions back into my model run and step back into Labelbox to compare these against the ground truth. Stepping back into the Labelbox platform and once again navigating to the model experiment that we set up, we will see, as before, the 1000 data rows. This time, however, stepping into it, we can see both the ground truth annotations and our model predictions. This allows us to visually compare how well our model is tracking against the ground truth. However, for a more quantitative approach, we can navigate to the metrics view in the top right hand corner. Selecting in here brings up the following view. We have high level metrics such as precision recall F1 and indeed in our case intersection over union, an important metric when assessing how well our predicted masks overlap the ground truth. In addition, we have various other views by which we can identify how well our model is performing. It may be of interest to iterate on our model by identifying where there are shortcomings. In this case, there are several instances of false negatives and indeed false positives. If we navigate to the false negatives, making sure to filter for where there are false negatives present, we can then identify various different instances of this. Stepping in, for example, in this case, we see the ground truth annotation suggests frayed edges. However, our model has not picked up on instances of frayed edges. What we can do to improve on this is to begin to select various instances where this is the case. So we can select instances such as these where frayed edges have not well been predicted by our model. Having done so, we can navigate to the top, find similar in catalog, and as before, we can leverage catalog's similarity functionality. In this case, however, we wish to set the threshold significantly higher. The idea being that we will narrow down on instances of our object where frayed edges exist, such as this. Once we've identified supplementary data that we may wish to annotate in order to improve on our model's shortcomings, we can do select all, and as before, we can send these to Annotate, send them to our defect tagging project, set the appropriate priority, in this case 1, the idea being that these will be served up first. Once we're happy, we can then click Submit Batch. This will send these additional data rows for annotation. We can repeat the process as we did before, bulking up our training data, and then we can create a second model run. What this will allow us to do is to train a second iteration of our model on the bulked up dataset. Having set up our second model run, appropriately exported the annotations via Python SDK, and trained a second iteration of our model, we can upload that model's predictions back into our second model run. Here, we join it as we've navigated back to our model experiment, reviewing model run 1, and what we can explore this time round is how we can compare model runs. Next to our existing model run, we can go and find the second model run that we have just created. Doing so will now allow us to compare the results across both models. Again, we can see the high-level metrics. However, navigating down, for example, to intersection over union, we can see that in the case of the chip, we've seen marginal improvement between our model runs. However, in the case of the frayed edges, since we bulked up with additional training data, the intersection over union score is significantly higher in our second model run versus our first. Doing this approach allows us to track over time with each model iteration whether or not we're seeing the intended improvement in performance that we would expect. It allows us to track the datasets used for each model and evaluate at which point we reach a model performance that we're comfortable deploying into production. Hopefully this overview demo has given you an idea of how you can leverage various capabilities across the Labelbox platform, from curation and exploration of our data, to annotation, through to model evaluation, and the feedback loop by which we can continue to improve our models over time.